Okay, I think we'll get started. So today in this lab, we're going to work with the DAC peripheral. So the PIC12F1822 is neat because it has an analog to digital converter, but it, like the PIC675 that we've been working with in the other series, but this also has a DAC. Now it's not a too sophisticated. It's a 32-bit DAC, but this can still be very valuable for all sorts of control. Obviously, we're not going to be able to make the most beautiful looking sine wave, for example, but still not too bad, 32-bit. Now, we are going to talk about several registers, and actually, I really chased my tail on this a lot. While the data sheet is quite good for these, I had a difficult time getting these all to work correctly, and there's a little bit of a counterintuitive thing going on here with the tris. So I'm going to try to point that out very carefully as we go through. So we're going to set up our PIC. We're going to use RA0 as the DAC output, so that's going to be an analog output. So we're going to need to tell the ANCEL register to turn that to an analog. That was one thing that stumbled me for a little bit, although I should have probably figured that out. And then we're just as kind of a check, we're going to just have a blinking GPIO pin here, so nothing special about RA2. We're just going to be using that. Okay, so what's cool is we get an output, and we have a little more sensitivity than just this, because we can use, as we're going to do today, the full voltage in as our range, and then what we will do is we will set in the DAC-CON1 register some fraction of 32 here, and that will represent a fraction of this voltage. And turns out it's pretty dead on, so that's nice. We can, though, have an external voltage. So let's say you just had 1 volt or 2 volts, then you can get a finer resolution of that if you didn't need all 5 volts. And you can do that also with an internal voltage. So a couple of versatile aspects here. We're going to just do this to kind of illustrate the principle behind this. The next lab, we will actually combine this with what we learned about in the previous lab with the lookup table and produce a triangle wave and a cosine wave. But here we're going to just swing between two. We're just going to alternate between two choices of voltage with a delay in between. So let's get to the computer and look at that. Okay, so we see it running right now, and I'm actually powering this with an external supply here, and you need to do that because if you have your PIC kit in, you can power it with the PIC kit, and I actually do have it powering with the PIC kit, so we'll be able to see the LED turn on and off. But the pin for R0 is used with the PIC kit 5. So we have to pull it out of circuit and run it. So we'll do that. So right now it's sitting out of circuit, and I've just chosen 2 voltages to swing between. So these are fractions of the full 5 volts. Okay, so let me pull the power plug here now, and I'm going to pull the chip, and I'm going to put it in position to be programmed. So now the PIC is powering things, but we would not read the right voltage off of pin 0. Okay, so let's go ahead and go to my GitHub page, PIC12F1822, and then we're going to go to DAC01, and we'll copy that. Now I'm because I want to go through carefully these registers, I have and I have not gone through the all the way from the beginning. So we've done this in a couple of videos in this series. The most recent one is Lab 7. So if you just want to go to get to this point, so how to choose the right controller, how to choose the right compiler, or assembler, and so on, consult one of the earlier videos, Lab 7, for example. So here we are, ready to go. So I'm just going to paste this in, and we have our code here now. So let's walk through the top parts, always the same as we've been using. So this is the configuration bits for the 1822. Then this is the resvec, so that just tells the PIC where to start. This is all going to be the same all throughout. And then we enter into the main part, not the main loop, but the part where we set the registers that we don't want to change. All of this is what we've been using, so the oscillator speed and so on. Now, we do need to change Ansel, and I said this was one of the areas I got stuck in. I blew right past this and left this as a 0, and that means it set all the pins are digital pins, and we want RA, let me spell analog from here, RA0 to be analog. Okay, now we want to change the tris. So this really fooled me here for a while, and in fact, I was stuck here, and it was ChatGPT, which honestly doesn't. It's okay at assembly, not very good, and I don't really use it. Use it for Python all the time, but I don't really use it for assembly. But I was just completely stuck on this, and why I was stuck is it was intuitive to me that pin 0 should be set as an output, but you actually have to set it as an input, which is crazy. So, and I did not pick that up in the data sheet. Now, it could be in there and I was just missing it, or I was just so fooled by my own thinking I knew what was going on that it should have been an output, but no, it's actually an input. So that's kind of interesting, I think. So then that sets the tris. Pin 2 is right here. That's what we're using for the blinker LED. Okay, so now let's look at the two important new registers, and these are on bank 2. So we need to do a bank select to go to the DAC 0, and let's walk through all these slowly and carefully here now. So bit 7 is what enables the DAC, and bit 5 enables RA as an output pin. So this is where I was thinking it was enough, and to have the tris as just leave that as an output. But apparently, when this is analog, then the tris has to say input, and then we use the 5th bit here as a 1 to enable RA0 as the DAC output. 6, not too important for our purposes. This is setting the low power state either as on or off. And so if you were in a power situation and most of the time you wanted the low end of your DAC, then you would set that for the low power state. If you wanted the high end of the DAC, you'd set that for the high power state. For us, it does not going to really matter too much. Then the bits 3, so where is that? 3 and 2. So 0, 1, 2, 3. These two here then. We set at 0, 0 will then reference to the input voltage. So the roughly 5 volts that are coming from the power supply. If we go 0, 1 there, we'll be using external voltage, and 1, 0 will be the internal reference. So this allows us to not use the full range, but I'm not going to go into that. That is discussed a little bit in the data sheet. Pits 4, and bits 1 are not used here in this register. So then we move that, so we turn this into the working register, then we move this into the DAC 0 register. Okay, so now we enter the loop, and so we need to set, we do a lot of switching of banks here. So we need to go to the bank with DAC 0, and that's also the bank of DAC 1. So I'm just using banks. I could have used 1 here. This is just to get to bank 2, basically. That's all this is doing. We're not actually going to change DAC 0. Okay, so now here's our choice of fraction of 32. So what is this? 8? 8, so 1/4. So basically a quarter of the voltage. Maybe, is that right? Yeah. And then that will be written to DAC on 1. So this will be, so we have the 5, 0, 1, 2, 3, 4. So here's our 5 bits. So we're using 8 out of 32 of the voltage here. That's going to be sent to DAC on 1. Now we have to do a couple, we have to move to the bank 0, and I just happen to remember port A is on bank 0, so that's what I just use all the time. And that's going to allow us to turn on the RA2 and call our delay. So our delay is this 3-loop delay that we've been using all the time in all of our series, and these registers are on bank 0. So in order to use the delay, we have to be on bank 0. If we were just switching back and forth and we weren't using the output pin or any of the delays, then we could stay on bank 2. So we'll call it a delay, then we'll switch back to bank 2, and then let's change this number. So what are we at here? So whatever this is. Okay, so this is going to be a higher value than, so we're gonna jump up to about 3 volts, almost a little under 4 volts. Move that to DAC on 1, so that will change the voltage on the DAC. Then we go back to pin 0, turn the LED off, and then delay again and swoop back around in this main loop. So let's go ahead, let me build this, make sure it builds, and let me write it. And it looks like it wrote. So I'm going to be careful here and not hot swap this. I've had some trouble with the this particular PIC that maybe it's just static, but I'm just a little extra careful here not to hot swap that out. Usually you can do that, it's okay. And if you got a bunch of these around, they're not too expensive, you could just keep your power supplies plugged in. But I've got them both unplugged here. And I will move this now to here. Now it's been moving these back and forth a lot, and I've been bending the pins. Okay, it looks like that's in. Okay, so now I'm going to bring our voltmeter back, and I'm going to plug this in. Let's see, maybe I can go to, let's do, no, I'm going to go back to here. Okay, so these are our 2 extreme values here as we go back and forth. Oh no, it's my batteries. Batteries are dead. So this is a way to change now the DAC, and so this is sort of the basic procedure. We will build upon this now in the next lab, and actually we'll call a lookup table and for a function, sine function and triangle function. So we'll get a triangle wave and a cosine wave, or a sine wave out of this.